Today I want to talk about evaluating learning algorithms and tuning learning algorithms so that they do the right thing, so that they do as well as possible when they're presented with novel data. So when you're working with machine learning, it's easy to lose sight of the fact that the goal is always to do as well as possible when you're classifying or when you're making predictions about data that you haven't seen yet, about data that doesn't even exist yet necessarily. So that makes life hard. How do you know if you're doing well if your metric for doing well requires you to have the data that you don't have? Well, there's one sort of simple standard thing that we can do, which is just to take our set of labeled training data. So this is the data that we have access to that we can use to train our algorithm, and we chop it into two pieces. A training set and a test set. The test set gets locked in the basement, hidden away, and we never look at it when we're training our learning algorithm. Only when we want to determine whether or not we're going to succeed, or whether or not we think we're doing a good job, do we pull out the test set. We run the test set through our learning algorithm, our trained learning algorithm. We see how well it does on predicting the labels that we know that test data has with it. And that gives us some sort of measurement of how well we think we'll do on the unobserved data from the real world. So the test set serves as our proxy for the unobserved data that we're hoping we're going to do well on in the future. So that's good. That gives us some way to have some confidence that we're learning something useful. But it still leaves us with the question of how exactly we should learn to solve the problem from the training set. And we have spent some time on that, right? We've looked at ways to pick parameters so that we can minimize error on the training set. Sometimes we can analytically find the best parameters. So if we're fitting a line to some data or we're fitting a polynomial to some data, we saw that we can find the exact parameters that will give us the least squares error on our training set. Sometimes we have to approximate that optimization problem, like when we're working with multi-layered neural networks. We can't exactly solve for the weights that will minimize our error, but we can use something like gradient descent to find a set of parameters that will do pretty well on the training set. So just let's actually think for a minute again about our example of fitting a line to some data. So let's just do that. Here's a little Python script that will fit a line to some data. Here's the data, these data points, right? This is a one-dimensional data set, so along this axis we have our independent variable, and on this axis we have our dependent variable. And we want to be able to make predictions, right, from our x-axis to our y-axis in the future. So here's the training data, and here's the best least squares fit of a line to this data. And you and I look at this data and we feel like it's probably not going to do, this line is probably not going to do a very good job of making predictions about unobserved data points, right? So if our x value is 2, then it looks like our prediction will be about 0.25 for this y value, but that doesn't seem right? It feels like the prediction should be up here somewhere. Well, a line probably doesn't represent the best model of this data, right? It doesn't appear to be linearly linear. So that's not too hard. We can, instead of fitting a line, we can fit some sort of polynomial. So we can try to fit a quadratic function to this data. We'll see what that looks like. And that's maybe a little bit better, but not a lot. So we can keep trying higher degree polynomials until we can get something that actually represents a decent fit. Oh, and that's looking pretty good, right? So a degree 3 polynomial starts to look like it's fitting this data fairly effectively. But there's nothing stopping us, there's nothing requiring us to stop at 3, even though this fit looks pretty decent. In fact, let's crank this all the way up to 12. We'll fit a degree 12 polynomial to this data set. That looks a little funny. Let's zoom in. And if you look carefully, you'll notice that now we've actually perfectly fit the data. So this line passes through all of the points in our training set. Success, right? This is a perfect fit to the data. Zero error remaining. But we have to remember that our goal is not to perfectly fit the training set. Our goal is to do well on the unobserved data, the data that we haven't seen yet. And I actually, let me do this. I'll plot the curve that this data was actually generated from, which is cheating a little bit, right? We can never see these true curves that the data comes from. But in a toy example like this, we can. So the dotted red line represents the true underlying distribution of the data, right? So what I did is I took that curve and I generated some points around that curve by randomly adding or subtracting a small amount to each point. So this is sort of, right, if I wanted the best possible fit for predicting future data points, that dotted red line would be the best possible fit. And you can see that this green line, even though it's perfectly fitting my training data, doesn't really look anything like the dotted red line. So I'm not doing well. And this is a very general issue that comes up with any kind of learning algorithm that you're going to try to develop. There's almost always some crank that we can turn that will make the learning algorithm more expressive or able to represent more complicated functions. And by turning that crank, we can almost always do better on our training set. But at some point, we end up overfitting. We end up representing details in the training set that are unimportant, that aren't representative of the actual real-world data, of the underlying data distribution. So the question then becomes, how do I decide how far to turn that crank? How do I decide how expressive to let my learning algorithm be? Right? So in this case, we could turn it all the way back down to a linear fit, but that seems to be going too far, right? There's real structure in this data that we're missing at that point. And in this case, it looks like this degree 3 polynomial is probably pretty good, right? That's a pretty decent fit to that data. But how can we sort of formalize that idea? Well, one nice way of thinking about it is through the use of a validation set. So there's a really good figure here. And in this particular picture, we're talking about multi-layer neural networks. So, a minute ago we were talking about fitting polynomials of different degrees. It turns out exactly the same kind of issue comes up when you're training a neural network in terms of how long you train it. So the longer you let your neural network train, the longer you run gradient descent, in general, the better you'll do on the training data up to a certain point. But eventually, you start learning information from your training data that actually isn't important, that isn't relevant to the learning task overall. And so what you end up seeing is something like this. Right? This gray line represents my performance on the training data set. So the longer I train my neural network, the better I do. Fantastic. The black line represents the training or the error on some other data set that isn't being used for training. So we would call this a validation training set. So now the normal thing to do, or a very typical thing to do, might be, rather than dividing all of my labeled data into 2 boxes, a training set and a test set, I divide it into 3 boxes, to 3 parts. A training set, which I use to optimize my parameters, a test set, which I keep locked in the basement until I want to find out how well I've done, and a validation set that I use while I'm training or while I'm deciding the parameters of my algorithm in order to tune the algorithm to do as well as possible. So in this case, right, this black line represents my error rate on a validation set. And it's telling me that I should probably stop training after, roughly 200 odd steps of training. Because beyond that point, I'm starting to do worse on the validation set, even though I continue to do better on the training set. And the idea is that the validation set is likely to be more representative of the test set. So what's happening when this line keeps going down? Well, it's hard to say exactly. The kind of thing that can happen is, let's say we've got a neural network that's learning to recognize written digits. And it's got a 1 with a little dot up in one of the corners, just a little speck from the camera that took the image. So if I let this thing train long enough, it might sort of reach the conclusion that since the only image that has a little dot in it is one of these 1s, that little dot is a really useful and important way of distinguishing between 1s and other kinds of digits, right? So between 1s and 2s, for example. So it's not, right? It's sort of an irrelevant detail, but if I let the neural network train long enough, it will sort of hone in on irrelevant details like that, which will cause it to do better and better on the training set, but it may cause it to do worse on the validation set. So that's one trick, and this trick of using a validation set sort of works across lots of different learning algorithms in lots of different ways of measuring kind of the complexity or the capacity of our algorithm. So we could as easily have plotted along this axis, the degree of a polynomial. So we could look at, as we fit higher and higher polynomial degrees, our training error will go down, but eventually our validation error will go up. This axis could represent the number of hidden units in a neural network, right? So as I add more and more hidden units to a neural network, it's able to learn more and more complicated functions, but at some point that becomes overkill, right? I'm learning details that aren't important. So I could create a plot like this using that on the x-axis. So that's one very general trick for tuning a learning algorithm, right? Keep this validation set and use that to determine the parameters. And throughout all of this, right, we're now thinking about this division between optimization, which is what we talked about during the last couple of lectures, right? This is given a model, given a neural network, or given the fact that we're trying to fit a line, how do I find the parameters for that model that give me the best possible fit? Now we're talking about model selection. So I'm not really interested in how I optimize a model. I'm interested in which model makes the most sense, which model will do as well as possible on the data. So we can think of this dimension here as representing the sort of complexity of my model. Another way of thinking of all of this is in terms of Occam's razor, right? So as I pick more and more complex models, I can do better and better at explaining my data, but I prefer simple explanations if they work. Let me bring up one additional idea, which is regularization. So regularization represents another way of kind of folding model selection into this optimization problem. So rather than using a validation set, what I might do is explicitly penalize complex models. Actually add something to my error function that makes it more expensive to fit a complicated model than it is to fit a simpler model. Here's a really simple example of that. So here's the error function we've seen a couple of times, the squared error function for fitting a line, or this could be for fitting a polynomial, etc. So this bit here is what we've seen all along, this bit on the left. This is new, right? And this is just saying that I'm penalized for making errors, but I'm also penalized for having large weights, right? These double lines represent essentially the length of that weight metric, that weight vector. So if this is 0, right, in a sense that's the sort of simplest possible model of this data, and this term will become 0. As these weights get big, right, that represents from a certain point of view, that represents a more complicated way of describing the data, and this error term goes up. And I can pick this parameter in order to sort of decide how much I want to penalize complicated models. And this is expressed here in terms of fitting a line or fitting a polynomial, but the same kind of trick can be used for neural networks. So this might be a weight penalty that I would apply to neural network learning. So I might have some sort of neural network with a bunch of inputs and a couple of outputs and a couple of hidden units, something like this. And if we think about what it means to sort of encourage these weights down here to be small, right? If a weight is 0, it's basically ignoring its input, right? It's not passing that information through. So I can do well by pushing down these weights by paying less attention to my inputs in a certain sense. And this isn't the only way to express a regularization terms, right? We can have lots of different sort of notions of a simplicity of a model. And to the extent that we can make that a number, a measurable number, if we add that to our error metric, then when we start minimizing our error metric, we're both minimizing our error on our training data and the simplicity of our model, or the complexity of our model.